So now this is where we bring in the notion of abstract interpretation. So here, so what we will do, right, is we are going to follow this very simple idea, right, that instead of maintaining an arbitrary set of states at each location, suppose we maintain an artificially constrained set of states, right, which are coming from an abstract domain D. Right? So essentially, we want to find out what are the set of program states which are reachable at every location. Right? But if we compute the exact set of states which are reachable at every location, then we will not. Then the procedure may not terminate. Right? So we are going to introduce this notion of an abstract domain D, right, where each element in the abstract domain D, right, it essentially is a set of program states, right, some set of program states. But now my constraint is that at every location I can only pick an element from the abstract domain D to express the set of reachable states at that location, right. So instead of being able to find the exact set of reachable states at that location, I can only pick an element from this abstract domain D, which hopefully will over approximate the set of actual reachable states at that location. Okay, so this is what we call as an abstract assertion map, right? So we compute this abstract inductive assertion map, which is mu hat, right? So earlier it was mu, right, which was from L to this sigma v, but now we have given up on actually finding the exact set of reachable states at every location, right? So instead of that, we are going to approximate it using this abstract domain D, right? So now we will compute this abstract inductive assertion map, which will be from L to D, right? So with every location we will associate a element from this abstract domain D, and this element will over approximate the set of actual reachable states at that location. Okay. So to make this more concrete, right, let's define this notion of states, right? So states, suppose, are the set of all possible program states, right? So we will call this as concrete states now to distinguish from abstract states, right? Because my abstract states are essentially going to be elements of the abstract domain D. Right? So a concrete state is the actual program state, right? So it's just a valuation of the program variables. Okay. So I'm also going to define two functions, right, which relate concrete states to abstract states. Okay. So once I have, let's say at some location, right, I have a set of concrete program states which are reachable at that location. I want to abstract it out into an element of the abstract domain, right? So that I will do using the abstraction function, right? So if I have, let's say, some set of states S which are reachable at this location L, right? But I cannot compute this set S, right? Because this may be infinite, right? It may take me, like it may take a non-terminating execution, right, to actually compute this set S, right? So instead I'm going to abstract it out with an element of the abstract domain, which is, let's say, D. But what is the relationship between S and D, right? So this relationship is computed through the abstraction function, right, which is S, which is alpha, right? So alpha of S is going to give me D, right? So in general, alpha is this abstraction function, right? So it takes a set of concrete states, right? So that's why it's a power set, right? So the domain of this function alpha is the power set of the set of states, right? So it's a set of program states, a set of concrete states to an element of the abstract domain, right? So the codomain is the abstract domain D, right? So associated with every set of program states is an element of the abstract domain, which is computed through the abstraction function. Similarly, I have the function in the opposite direction, which is the concretization function, right? So which is that given a set of abstract, so given the abstract domain, right, which is D, right, I want to associate every element in the abstract domain with the set of concrete states that this particular domain, that this particular element is abstracting out, right? So this gamma, right, this is going to be a function from D to the power set of states, right? So it's going to associate every abstract element D, right, with the set of concrete program states, right, that are being abstracted out by this element D. Okay, so this is the abstraction and the concretization function, right? And using this abstraction and the concretization function, right, so where is it used, right? So we want to compute this mu hat, right, which is at every location in the program we want to associate an element of the abstract domain, which will over approximate the set of reachable states at every location, right? So I know that the set of states which are reachable at every location, the set of, so these are concrete program states, right? So the set of concrete program states that are reachable at every location are given by this concrete inductive assertion map, right, which is mu of L. So mu of L is the concrete inductive assertion map, right? So it's computing the exact set of concrete program states reachable at the location L. Mu hat of L is the abstract inductive assertion map, right? So it's computing an abstract element, right, or an element of the abstract domain, right? What is the relationship between these two? So I can define the relationship between these two using the abstraction and the concretization functions, right? So in particular, I know that if I concretize, right, this mu hat of L, right? So mu hat of L, remember, is an element of the abstract domain. By concretizing it, I am essentially saying what are the set of concrete program states which are associated with this abstract with this element of the abstract domain, right? So this mu hat of L is going to be, let's say, some D, right? So I'm going to ask, okay, what are the actual set of program states which are associated with this element D, and this must be a superset of mu of L, right? Because the abstract domain, right, it must over approximate the set of actual the concrete program states which are reachable at the location L, right? So for every location L, mu of L must be a subset of gamma of mu hat of L. Okay, so this is the correctness property, right, that we want abstract interpretation to satisfy, right, which is that for every location L, mu of L must be a subset of gamma of mu hat of L. Furthermore, right, in order to compute this abstract inductive assertion map, right, we are essentially going to again execute the program, but using the abstract strongest postcondition operator, right? So earlier we had used the concrete strongest postcondition operator, right? Remember, so this concrete strongest postcondition operator, this SP, right, takes as input a formula and a command, right, where a formula encodes a set of program states, right, and it essentially gives you another formula which will encode the set of states reachable after executing C on any state in F, right? But now instead of having a formula, I am going to have an element of the abstract domain, right? So I'm going to have an element of the abstract domain, let's say D, and then I'm going to ask, okay, suppose I execute the program command C, right, on the set of all concrete program states which are abstracted out by this element D. What is the new value, right? What is the new value of the abstract domain, which is going to again abstract out the set of reachable program states, right? So this SP hat, this is, right, this is going to be a function from D cross C to D, right? So it's going to essentially tell me how to execute the program command C, but in the abstract domain, okay? And again, right, you can sort of think about how this should be related to the concrete program states, right? So given an element of the abstract domain, right, I know that I can concretize it using the concretization function, right? So suppose I concretize D, okay? So the question is how should I relate, right, this SP hat of D comma C, okay, with the concrete strongest postcondition operator, right, which is SP. So SP hat of D of C is going to be another element of the abstract domain, right? Now let's say if I compute the strongest postcondition and this is in the concrete domain, right, over the command C, then my concretization of SP hat of D comma C must be a superset of SP of gamma of D comma C, right? So why is this the case? Because this SP hat of D comma C, right, this should over approximate the set of states which are reachable after executing C on any state that is abstracted out by D, right? So I know that the set of states which are abstracted out by D are essentially gamma of D, right? The set of states obtained by executing C on any state in gamma of D is SP of gamma of D comma C. So therefore my SP hat of D of C should over approximate all those states, which means that the concretization of SP hat of D comma C should contain SP of gamma of D comma C, right? So this particular property must be followed by the abstract strongest postcondition operator, which is SP hat, okay? So just to kind of summarize, right, what we have done so far. So we have associated an element of the abstract domain with every program location, right? And now instead of computing the actual reachable states at every location, we want to compute the abstract values that are reachable at that location, right? But the abstract values must over approximate the concrete values, and we formally define that by using the concretization function gamma, right. So we say that this gamma of mu hat of L must be a superset of mu of L, and in order to compute this mu hat of L, we are going to use the abstract strongest postcondition operator, right, which is SP hat, but this SP hat should also satisfy the fact that it over approximates the effect of the concrete strongest postcondition operator. So now we can simply modify this forward propagate algorithm, right, in order to use the abstract domain instead of the concrete domain. Right? So instead of operating over the concrete set of program states, let us operate over the abstract domain. Right? So instead of computing this mu of L, which is the concrete inductive assertion map, we are instead going to compute mu hat of L, and the only difference is that instead of using, so now this mu hat of L, right, mu hat is now a function from L to D, right. So we are going to associate an element of the abstract domain with every location, and instead of using the strongest postcondition operator, we are going to use the abstract strongest postcondition operator, right, which is SP hat. So by a very simple change, right, we will keep this algorithm as it is, but instead of executing this algorithm on the concrete set of program states, we will execute it over the abstract domain. So these are the minimal changes in the algorithm, right, which so this will convert the forward propagate algorithm to the abstract forward propagate algorithm, right, which is where we are again executing the program in the forward direction to find the reachable states at every program location, but using the abstract domain, right. So now the changes that I have made, right, I have highlighted them in red, right. So the first change, right, is that at the location L0, right, this abstract inductive assertion map, which is mu hat, is going to initialize it with alpha of P, right. So remember, P is the set of program states at the beginning of the program, right, at the start location L0, but P is some arbitrary formula, right. So we cannot express such an arbitrary formula, right. So we must use an element of the abstract domain to express the set of states which are encoded by this formula P, and I get that by essentially applying the abstraction function, right. So remember the abstraction function, right, this is from the set of program states to element of the abstract domain, right. So by applying the abstraction function on P, I get the appropriate element of the abstract domain which I need to initialize at the location L0, right. The rest of the rest of the algorithm remains the same, except that at this point, right, where instead of using the concrete strongest postcondition operator, I use the abstract strongest postcondition operator. Okay. Now there are two more interesting changes here, right. So remember that once I calculate this F, right, which are the new set of program states, right, which are reachable at the location L prime in this case, right, I need to ask, okay, does mu of L prime, does it already contain F or not, right. So essentially I am asking whether or not F, right, let's say is a set of program states, is it contained inside mu of L prime. Earlier I had used this formula, right, F implies mu of L prime, because I was expressing a set of program states using formulas, but now I am expressing them a set of program states using elements of the abstract domain, right. So here F is going to be an element of the abstract domain, mu of L prime is going to be another element of the abstract domain. So I cannot use implication, right. So instead I am going to define an ordering over elements of the abstract domain, right. So less than or equal to is an ordering over the elements of the abstract domain, right. So I'll ask, okay, is F less than or equal to mu of L prime, okay. So if F is less than or equal to mu of L prime, remember where F and mu of L prime are both elements of the abstract domain, right. So if it is the case that F is less than or equal to mu of L prime, then that means that the set of program states which are abstracted out by F are already contained inside mu of L prime, right. So essentially this means that gamma of F is a subset of gamma of mu of L prime, right. So if you concretize the abstract domain, so if you concretize the element F of the abstract domain, and if you concretize the element mu of L prime of the abstract domain, it is the case that gamma of F is contained inside gamma of mu of L prime, and therefore I don't need to change mu of L prime at all, right. So what I have, so this is a special ordering constraint, right, that I require on the elements of the abstract domain, and this is the ordering constraint that I am using here, right. So if it is not the case, right, so if F is not less than or equal to mu hat of L prime, that means that I have computed a new state, right, which is reachable at the location L prime. Then I need to add that particular state, right, which is F, to the inductive assertion map at the location L prime, right. So this addition, right, we do using this another operator which we will call as the join operator, right. So again, if you recall, right, when we were using formulas, right, we had defined this mu of L prime as mu of L prime or F, right? So we were using disjunction here. But now I cannot use disjunction because F and mu of L prime are no longer formulas, right? They are elements of the abstract domain. So I'm going to define this operator which I call as a join operator, and this is going to be a function, it's going to be a binary function over elements of the abstract domain, right? So it takes as input two elements of the abstract domain and computes their join, okay. So I am using the join function here. Mu hat of L prime will be updated to mu hat of L prime join with F. And again, you can imagine what will be the property that we will want this join to satisfy, right? So if I have two elements of the abstract domain, right, let's say d1 and d2, and if I take their join, then gamma of d1 join d2, right, it must be a superset of gamma of d1 union gamma of d2, right? Because, so what I want to say is that this d1 join d2 is another element of the abstract domain such that it should over approximate, right, the set of the set of concrete program states which are contained or which are abstracted out by d1 and d2, right. So gamma of d1 are the program states which are abstracted out by d1, gamma of d2 are the program states which are abstracted out by d2. Their union, right, I want to abstract out their union. So in order to abstract out their union, I will compute the join, which is d1 join d2, and it must be the case that this particular element, right, so this is another element of the abstract domain, right. So this element must over approximate the set of concrete program states which are abstracted out by d1 and d2, okay. So again, right, just to summarize, right, we are essentially using the same forward propagate algorithm, right, but now we are executing the program in the forward direction over the abstract domain, and we have added two more. So aside from requiring the abstraction function alpha, the concretization function gamma, and this abstract strongest post condition operator which is SP hat, I need these three things, but I also need two more things, right. One is this ordering which is less than or equal to, right, the ordering over the elements of the abstract domain, right. So this is going to be a relation, right, over the elements of the abstract domain, okay. And I also need this function, right, which is the join operator over elements of the abstract domain, right. So if I have all these things, right, then I can execute this abstract forward propagate algorithm and I can execute the program in the forward direction, but in the over the abstract domain D, okay. So what we are going to do is we are going to use this particular mathematical structure which is called a lattice, right. So we are going to say that this abstract domain D is going to be a lattice, and the advantage of doing that is that a lattice defines both of these things, right. So by definition, right, a lattice is a partial order, as we will see, right. So therefore a lattice by itself contains this less than or equal to or the ordering relation over the elements of the domain, and it also contains this join operator, right. So a lattice defines both the ordering operation and the join operation, right, over the elements of the abstract domain, right. So that two of the requirements that I had mentioned, right, which is this less than or equal to and join, this will be automatically fulfilled if my abstract domain is a lattice, okay. And I need both of these things in the abstract forward propagate algorithm, okay. The rest of the things are still needed, right. So I need the abstraction function, the concretization function, and the abstract strongest post condition operator, okay. So now once you perform this abstract forward propagate algorithm, right, so you will compute some mu hat of LE, and now all you need to ask is whether or not this mu hat of LE, does it contain the or rather is it contained inside the set of program states Q, right. So in the sense that if you were to, let's say, concretize this mu hat of LE, right, is it the case that its concretization is contained inside the set Q, right. So if it is contained inside the set Q, the way we have defined this mu hat of LE, we know that it over approximates the set of actual reachable states at the program location LE, right. So I know that mu of LE, right, which is the concrete inductive assertion map, right. So this is the exact set of reachable program states at the location LE. This is a subset of gamma of mu hat of LE. So if I know that gamma of mu hat of LE is a subset of Q, then from this I can infer that mu of LE is a subset of Q, and therefore the whole triple PCQ is valid, right. So I have another verification procedure now, right. So now instead of operating over the concrete program states, I can operate over the abstract states, and I can ask whether or not this gamma of mu hat of LE, right, is it a subset of Q. Equivalently, right, we can also ask this thing, right? So we can, instead of concretizing this mu hat of LE, I can abstract Q, right? So I can ask whether or not mu hat of LE, is it less than or equal to Q, right? So here I am using the ordering over the elements of the abstract domain, right? So it's less than or equal to alpha of Q. Okay. So you can use either of these two things, and you get another verification procedure. Okay. So let me just quickly illustrate, right, this abstract forward propagate using the same example, right, that we saw earlier. Right? So we saw that forward propagate on this particular program, it doesn't terminate, right, because it keeps on discovering new program states at the location L1. Right? So computing the exact set of program states at the location L1, right, is not possible using the forward propagate algorithm. So let us now use the abstract forward propagate algorithm, right, and suppose we want to only prove this post condition, right. So we want to prove that when this program terminates at the exit location, the value of I is always positive, right? So I is always greater than or equal to 0. So I don't care about what are the exact values of I at the end location, but all I want to know is in every execution of this program at the end location LE, the value of I must be positive, right. So any execution which terminates, right, must terminate in a program state where the value of I is positive. Okay. So in order to compute, or in order to verify this particular post condition, I am going to introduce an abstract domain which I call as the sign abstract domain, right. So here, since I am only interested in whether or not the variable is positive or negative, I am only going to maintain the sign of the variable I, right. Is the variable I positive or negative, right. So this abstract domain D, right, remember I said that I am going to associate an element of the abstract domain with every location in the program, right. So what are the elements of this abstract domain? So there are 4 elements, right, plus minus and bot. Okay. So here this is not false, right, but this we will pronounce as bot. Okay, and we will see why we call it as bot later on. Okay, but essentially, right, this plus minus is over approximating the set of all possible program states, right. So plus minus means that the variable I can take any value, right, which is true. So this is the formula true. Okay, so it's saying that I can take any value, while plus is over approximating, or plus is approximating those concrete program states where the value of I is greater than or equal to 0. Right? So I don't care about what is the exact value of the variable I, right, but the entire set of program states where the value of I is positive, that is approximated by a single element of the abstract domain, right, which is just this element plus. Right? Similarly, minus is approximating the all the program states, or is abstracting out all the program states where the value of I is negative, right, it's less than 0, right. And for bot, we just say that the gamma of bot is bot, where this bot is actually the formula false, right. So it's essentially abstracting the empty set of program states, right, or the formula false, right. So no program state satisfies the formula false, and therefore gamma of bot is actually false, right. So bot is abstracting out the empty set of program states. So now let me execute this abstract forward propagate algorithm, right, over this particular sign abstract domain, right. So initially I am going to start with the value plus minus at the location L0, which means that I can take any value, and now the abstract forward propagate algorithm will propagate this abstract value plus minus from L0 to L1, right, by executing this particular program statement, right. So we want to compute SP hat of I equal to 0 and plus minus, right. So again, essentially what we are asking is, if you execute I equal to 0, what are all the concrete program states that you can get, and what is the best value from the abstract domain which can be used to over approximate that set of program states, right. So I know that if I execute I equal to 0, I will contain only one value, which is 0, right, and there is only one element. So there are two elements of the abstract domain that I can use to over approximate that particular state, right. I can either use plus minus or I can use plus, but plus is better, right, because plus is saying I is greater than or equal to 0, which includes I equal to 0, right. So therefore on executing this, I am going to get plus here at the location L1, right. So at the location L1, I am going to say that the inductive assertion map, right, the abstract inductive assertion map, it maintains the abstract value plus. Okay. So next I propagate from L1 to L2, right. So remember that L1, so at L1 I know that all the value of I is plus, right, which means it's greater than or equal to 0. If I execute this assume I is less than n, remember assume only filters out the program states, right. So it only allow a subset of the program states which are at the location L1 to reach L2. But since every program state at location L1 has I positive, therefore I will continue to remain positive at the location L2. Right? So at location L2 as well, the abstract inductive assertion map will be plus. Now from L2 back to L1, I need to propagate plus, right? So I know that the value of I is positive at location L2. If I execute I equal to I plus 1, I am just adding 1. So the value of I will continue to remain positive, right? So therefore I will get plus again. So therefore this plus will not change, right? So essentially now since this plus doesn't change, right? If you again do another pass, right? If you again propagate from L1 back to L2, you will get plus again at L2 and then plus again at L1, right? So essentially we have reached what we call a fixed point, right? And we'll define this later as well. So once you have plus, I again propagate this plus from L1 to LE, right? But again, since this is assumed statement, right? So it will only filter out a subset of the program states from L1 to LE. So therefore, it will continue to remain plus at LE as well. Right? So I will get plus. So this is the abstract inductive assertion map for this program, right? Which assigns plus to all of the program locations, right? L1, L2, and LE, right? And which means that at the location LE, the value of the variable I is guaranteed to be greater than or equal to 0, which is exactly what we wanted to prove, right? So this was our post condition, right? So you can see that we have overcome this problem, right, of the non-termination of the forward propagate algorithm, right, by ensuring that we are only keeping track of the abstract values which are reachable at every location, right? And in this case, our abstract domain, which is the sign abstract domain, is good enough for us to prove the post condition, right, which is that the value of I is positive at the location LE. Okay. Okay, so we will end here, and in the next lecture, right, we will try to formally define this notion of abstract interpretation, right? What are some of the desirable properties that we require out of abstract interpretation? Okay, thank you.